Hello to everyone that's attending this conference. I'm José Lopes. I'm finishing my master's degree in the University of Minho in Portugal, and I'll be presenting the paper I made with Regina, Sousa, António, Abelha, and José Machado, all working in the Algorithmic Research Center and active members of the university's community. The paper, as you all can see, is entitled Big Data in Healthcare Institutions, an Architecture Proposal. In this presentation, I'll initially introduce the big data topic, giving some context and motivation. I'll speak about the main concepts regarding the subject. Then I'll show the proposed architecture, explain its process, and finally discuss it and take some conclusions. So, giving some kind of an introduction to the paper subject. We know that medicine is heavily linked to technology, in such a way that it can be considered dependent on it. These technological innovations have guaranteed improvements in terms of quality of life and of reduced costs in the services provided by it. Taking this into consideration, institutions are now focusing in medicine that is both preventive and predictive, and not only based in the interpretation of symptoms. We also know that all the available data in healthcare institutions is relevant. So it's important to collect and store this data for the construction of knowledge and its consequent evolution. This will lead to an enormous amount of information in its raw state, and its continuous generation is what defines the concept of big data. Now, the reasons why we developed this paper are the fact that the existing data management tools don't have an ideal behavior for processing big data, and the fact that there is a lack of sensitivity for the health area. Consequently, this paper provides a study about the problem of knowledge construction from big data in healthcare institutions and an architecture that deals with the challenges of big data in the health area. After the introduction of the origin of the big data concept, I'll now talk about its insertion in healthcare institutions, its potential challenges, and associated data sources. Then I'll talk about the usual big data engine, that is Hadoop, and its advantages related to the healthcare institutions. So, as I previously said, healthcare institutions generate large amounts of data. However, this data is not always in its digital format, so its processing is a bit more difficult. Additionally, new forms of data, such as biometric sensors and 3D images, are available, so it's necessary to digitalize all these types of data. The most important branches that I defined as priority research subjects are the support of research in a genetic context, the transformation of data into information, and the support for self-care. On the other hand, big data has its challenges, namely the resistance to change by health professionals. It requires considerable investment, and that investment has no certainty of return. There are also some issues concerning privacy, data security, and data ownership. The data sources of healthcare institutions are shown in this graph. We have billing data, that is data that documents the patient's symptoms, clinical records, and laboratory results. We have laboratory data, drug records, clinical notes, medical images that are usually large in size and complex. We have documentation of reports and tests, and finally, sensor devices. The most common and most researched big data engine is Hadoop. It manages the processing and storage of data in a scalable computer server clusters. It is the center of an ecosystem of big data technologies that collect, analyze, and manage databases, and is the usual choice for big data due to its high level of durability and availability. Its advantages are scalability, flexibility, low cost, fault tolerance, and the need of less computer power. And its advantages are related to its security, stability issues, and the fact that it is not an ideal tool for small amounts of data. Concerning healthcare institutions, most of them are still studying which are the most appropriate big data tools, but Hadoop is an advantageous solution, given the fact that it allows the storage and availability of data without huge costs, and that it can function both as a data organizer and data analyst. The following section is related to the architecture proposal in the paper. So the goal is to create an open source architecture for capturing and processing in real time large volumes of data that are related to the healthcare area. In order to do this, I'll talk about the structure of the architecture and its many layers. Then I'll present all the open source tools, and now we will proceed in terms of monitoring, alerting, and security. Finally, I'll explain the whole process. That is basically how the data flows in the architecture. As we can see, the architecture is divided in 5 layers that will be explained in greater detail in the following slides. We then have the data layer, the data aggregation layer, the data analytics layer, the information exploration layer, and the data security layer. In terms of monitoring and alerting, this will be inserted in the information exploration layer. First, we have the data layer. That is basically the data sources for this framework. The idea is to collect huge volumes of data in all its formats and from various healthcare sources like physiological signs, laboratory results, electronic records, and prescriptions. Then there's the data aggregation layer. Here we collect, transform, and store all the data. The objective is to collect high quality, accurate data for better and more relevant results. This layer contains 3 substructures, as seen here: the data collection, the data storage, and the ETL process. So first we have data collection. The data collection engine decides how the data is collected in order to build the data pipeline. It can be then defined as the extraction portion of the ETL process that is explained next. So the ETL process stands for extract, transform, load, and tries to systematically process data in order to make it available in a more accessible format. The extraction is related to the data collection substructure, where data is extracted from different sources. The transformation step turns the data into a specific and required format, and the load step is just the loading of the processed data into its destination, which is usually a database or a distributed file system. The final substructure is data storage, where the data programmed for batch processing is stored in a distributed file store. This is important for storing high volumes of large files. The data aggregation layer is followed by the data analytics layer, where we process and examine all the collected data through 2 different types of processing. First, we have batch processing, with which we can process huge amounts of data at once, and stream processing, which allows us to analyze the collected data in real time. The next layer is information exploration. Here we take the processed data, find value in its patterns and relations, and extract business intelligence. It is also in this layer that we provide an user-friendly representation of the data-driven outcomes. This is mainly done through graphs, tables, and images. Now that I've explained the layers, I'll talk about data security after this. I'll speak a bit about the tools that will be used in each layer. Firstly, we have Apache Kafka. In this context, Kafka will work both as a data ingestion and a stream processing tool. Kafka works as a platform for a real-time environment that is used mainly for data pipelines, stream processing, log aggregation, and data integration. Kafka is heavily used due to its many advantages. Fundamentally, its low latency, high throughput, fault tolerance, distributed architecture, scalability, and real-time handling. Its most important disadvantages are the fact that it doesn't have a complete collection of management and collecting tools, and that its performance decreases as additional processing is required. Then there's Talent. It supports ETL-oriented implementations for on-premises deployment and for a software as a service model. Talent is a very helpful tool concerning the ETL process because it has a drag-and-drop user interface and pre-built connectors and components. So, in terms of its advantages, it's a flexible and scalable solution for manipulating and extracting big data. It enables users to access, transform, move, and synchronize data through several big data components. And as I said before, it has a user interface that allows us to drag and drop and configure components. HDFS, which stands for Hadoop Distributed File System, is connected to the data storage substructure of the architecture. As its name suggests, it is a distributed and scalable file system, and it is the primary data storage system used by Hadoop applications. It provides many benefits, such as its scalability, high fault tolerance, and large data storage. It can be implemented on low cost and easily replaceable hardware, and is built for high data throughput and optimized for MapReduce workloads. MapReduce is a batch processing tool that will be used in this architecture. So, MapReduce allows the scalability of service, called nodes, in a Hadoop cluster, and its purpose is to split the collected data into smaller and independent parts that will be processed in parallel, which reduces the processing time. As I said in the HDFS's advantages, since it works in the same servers as HDFS, it allows faster data processing. Other important advantages are the ability of parallel processing, its scalability, flexibility, availability, and fault tolerance. The last tool in the architecture is Tableau, and is connected to the information exploration layer. Tableau is a tool usually used for modern business intelligence that turns the processed data into useful insights, which are helpful in the decision-making process. Its main advantages are its simplicity, high performance, its ability to connect to various data sources, and its visualization capabilities. However, it's also associated with a higher cost and has limited data pre-processing. Monitoring and alerting are also connected to the information exploration layer. First, we have monitoring. It basically tries to identify faults and assists in their elimination. In the architecture, the monitoring process is done through reports. In these reports, we organize the retrieved data into dashboards, charts, tables, and time series to keep track of the data's performance. Then we have the alerting process that is connected to the monitoring system and detects and notifies users when there is unexpected changes in the system state. In the architecture, reports will alert through warnings and notifications when data fall outside expected ranges or predefined criteria. With the help of these alerts, we can take immediate action if necessary. Now for the last layer, which is data security. Data security is tied to vital activities that manage the access to the system's data and services. It involves authentication, that is related to the verification and validation of the user's or services identities. Connecting to the tools used in the architecture. In Hadoop, authentication is done with Kerberos and LDAP, which is a directory access protocol. Other big data tools use SAML, OAuth, and HTTP authentication. And authentication in Kafka is done with SSL or SASL. Then there's authorization, that makes sure that the user or process has the rights to access resources or services. For example, the access to HDFS is managed through Unix access rights, and authorization in Kafka is controlled by ACLs. Data protection is also important in data security and normally concerns data encryption and data masking that prevent the access to sensitive data by unauthorized users or applications. Encryption in the HDFS is provided by Hadoop and in Kafka by the usage of SSL and TLS. The last topic concerning data security is auditing, that monitors the activity of an authenticated and authorized user or process, and monitors when data is accessed, added, or modified. Every Hadoop component offers audit capabilities that guarantee that the users and administrators' activities can be logged. Also, all the big data components allow logging to the local file system or into HDFS. After I've explained all the layers and associated tools, I'll quickly clarify the data flow process. So the idea is to have a hybrid architecture, meaning that this architecture is capable of both batch and stream processing, so we can visualize information in real time. First, there's the healthcare data sources in the data layer. Kafka connects to this data and delivers real-time ingestion here in the data collection substructure of the data aggregation layer. Since we can't perform ETL transformations to Kafka, the collected data goes from Kafka to Talend using its standard connectors and components. Talend will perform the user's required ETL transformations and writes this data in HDFS, working as a data storage. After this, data can be processed by MapReduce, which will take charge of the batch processing, or sent again to Kafka, that will perform stream processing. MapReduce's data can again be stored in an HDFS after processing if the user requires it. After processing data, we can explore the acquired information through Tableau. Tableau connects to Kafka that performs stream processing, which makes it possible to obtain real-time results that will be continuously updated as new data is ingested and processed. However, as I previously said, Tableau is associated with a higher cost. So, in order to get around this problem, it is advantageous to make use of our own tool. So Tableau would construct the evaluation parameters, and we will then view and manipulate these parameters on the tools we designed, where we could, for example, construct warnings based on the information acquired from Tableau. Lastly, I'll discuss and present some conclusions related to the big data subject and the proposed architecture. And in the end, I'll talk about possible future work. Looking into the proposed architecture, we can see that it is capable of supporting healthcare analytics by providing batch and real-time results, and with the usage of HDFS, it's also a storage technology solution. Its hybrid structure allows the ability to combine historical data and real-time data and allows us to produce real-time results. And with the usage of Kafka as a stream processing tool, we can handle healthcare data that require an almost immediate response. We can conclude that this architecture is associated to a high level of implementation complexity. Firstly, because of the volumes of historical data being continuously produced, that will make it difficult to maintain the production of real-time results. And because of the difficulty of using different technologies for batch and stream processing. Since MapReduce and Kafka are developed separately, it requires higher efforts to implement the proposed architecture. It is also important to note that other open source tools are available. So for data collection, we could use Apache Flume and Apache NiFi, and other stream processing systems are Apache Spark, Apache Flink, and Apache Storm. Finally, future work basically concerns the practical implementation of the proposed architecture, so as to evaluate its performance and see the benefits of its usage when dealing with huge amounts of healthcare data. With that, I end this presentation. Thank you all for your time, and I hope you enjoyed this subject.